kind of adjusted the plans accordingly for our remaining half an hour here. Everyone say hello, Oliver.
Hello.
We hope you're
Monday.
quote feeling better.
Can I say something? Sunday, I'm sorry I kind of sold you out, but yeah.
Yeah.
He's in Florida right now.
Sunday, we need to work on our physics.
Okay. All right.
But he told the school he's telling the school he's sick. Like, you can't approve like a vacation.
Yeah.
So we'd like you to know that this news is now on the internet for all to recognize. Okay.
We're sending this to Miss Lau.
Yes, we're sending this to Miss Lau.
This is like another story to like.
But wait,
she's a.
All right. We left off with talking about, okay, let's listen, please. We left off talking about solving this differential equation. This was, just to recap, we ended up here. And we said that we could leave the solution this way. But I am going to we're going to talk through how we can rewrite solutions like this, where, by the way, let's remember, we had complex values for r, right? And so we're going to do this, and just to be clear, when we get to the final end, there's no need for you to ever duplicate this algorithm, but it is important for you to see. And then, at the end of this, we're going to talk about the Wronskian. That was kind of the word I was hoping for the effect, Eric. The Wronskian.
Whoa.
It's Wronskian. That's a test. That is a test for linear independence, and we'll talk about that in a minute. Also, remind me too, so we don't leave anything. The fact that we can linearly combine two solutions for a general solution is verified and justified by the principle of superposition. Okay, so don't forget, this right here is a result of the principle of superposition. Okay. Here we go. Let's dive in. We're gonna get into kind of the arduous algebra here. All right. We're gonna take this general solution in conjunction with Euler's formula and reframe this solution. So I'm gonna meet you where I am gonna just play with some exponents for a moment. Is that better if you do that, Robbie?
There's a ton of glare.
A ton of glare. Oh, I see. Okay. All right.
What if you put it on the side?
Yeah, because no one.
Oh.
Yeah.
Okay. I'm close.
Okay.
Now I'm
Here we go. Are you ready? Let's go. Y equals, okay, C1. Now, look what I'm going to do. I'm going to distribute the x and tease apart that sum, all right, which means, let me just think about how to best do this. Hang on a minute. Let me think about how to best. 1 minute. Okay, all right. Let's do this. Ready? This becomes e to the negative x times e to the I root 2x. Do you agree? Okay, plus, here we go. C2 e to the negative x times e to the I root 2x. Okay? I just heard that there's a really great statement someone made a link someone sent me recently, that the most arduous thing about a diffie-Q's class is kind of the algebra, and calculus is fairly basic, but the algebra, yes, what's the matter, Max? What's the matter?
They don't have different signs.
Oh, yeah, this one should be negative. Yeah, thank you. I just lost that negative. So the negative up here, right? Yeah, good point. Thank you. Good catch. Very good. All right. Now, are you ready? Here's what we're going to do. We're going to do this correctly, all of us together. We are going to replace each of these, e to the x times something I, right, with this appropriately and correctly. Okay? So, in Euler's definition, e to the ix, yes, Jeannie?
Oh, I was just going to say, this is like a tiny detail, but I think that it was root negative 2. Is that oh, no, we took out the I step.
This is yeah.
Everyone okay?
Wait, I'm actually.
What's the matter? What's the matter?
Oh.
But you
Same base, when you're multiplying, you add exponents.
Oh, no, okay.
Everyone okay with the algebra? All right, here we go. You ready? We are going to replace each of these e to the power of I terms with this expression right here, okay? So everywhere you see an x here, it's going to be root 2x. Do you understand? Because this is e to the ix. We're doing e to the I root 2x, okay? So we're going to do this. Ready? Come on down. Here we go. Y equals C1 e to the negative x times, okay? cosine of root 2x plus I sine of root 2x. Everyone good? Come on over. Plus C2, and if we just hang tight with me here, please. The result is so worth it, I promise. Minus I sine root 2x. Everyone okay? Okay? Everyone okay? What's the matter? We good? All right. One more time. This negative? That came from up here, Connor. So it's plus a negative, if you will. That negative here came from right here. Can you see a little pointer?
Yeah.
A little, yeah. Do you see it, Connor?
That's just I.
I.
Okay, sorry.
Okay.
It's like an imaginary.
Really important. Those of you who were in class yesterday, did you watch the derivation of Euler's formula? Was it like mind blowing? Yeah, like the yes, and like the woman who tattooed the thing on her back,
I thought it was branding.
branded, whatever it was. Different what?
I'll brand myself for the
Yes. Is it bothering you, Jeannie? Yes, I will. Yes. Yes. I sometimes think that I can. Yes, you're right. Like it's disturbing. Is that what you're saying, Jeannie?
That's what I did yesterday.
Yeah, a little bit.
Yeah.
I see this like a picture like circulating forward. I was like, oh.
Well, here's the thing. What's interesting is that's disturbing. Here's the interesting thing, though. You know what? In some, I mean, there are. This is like an expression of like personal expression of fashion and beauty, right? I mean, you're kind of projecting pain. It doesn't necessarily mean it's painful.
I mean, it was.
Oh, no, it was-
But yes.
Well, I mean,
You don't know that necessarily. You never know that.
A little morphine things.
All right, here we go. Okay, Nick, thank you very much. All right, ready? Here we go. Let's keep going with the algebra. I'm going to factor e to the negative x out of both of these, and then at the same time, distribute C1 and C2. So just be really careful. E to the negative x is factored out of the whole thing. Then I'm going C1 cos radical 2x plus C1 I sine root 2x plus C2 cos root of 2x. Oh, you want to know what, everyone?
Yeah.
Please.
Yeah, hang on a second. Remember I was talking about the algebra thing? You know what? This is such a dingbat thing I just did. Look at this. I'm just an idiot. Look. Do you see how, look over here? You know how this is e to the x times I, right? But it's negative radical 2x, so I just realized this should be a negative argument inside here, and then plus the negative argument there. Yeah, that makes, I just realized, I just caught that when I looked at this. Does that make sense, everyone? Yeah, thank you, yeah. And I think, Connor, your question, like, maybe kind of subliminally go and just like, is that algebra actually correct? Plus C2. Mm-hmm, okay. Everyone all right? It's a little bit sloppy because it's not clear that this is the argument. Just hang on. Let me just clean this for a minute. Hang on a minute. Plus C2 times I times the sine of negative radical 2x. Everyone all right? All right. However, even odd properties of the cosine and sine function. The cosine of theta versus the cos of negative theta, they are... Oh my goodness. They are the same. Cos of theta and cos of negative theta are equivalent because if you think of the quadrants of the angles, all students take chemistry, whatever it is, right?
All students take calculus.
Okay, yeah, okay, very good. Yes, thank you. So then we have e to the negative x. Come with me, please. This is C1 cos of radical 2x plus C1 I sine of radical 2x plus C2 cos of radical 2x. See how I just made that clear to myself? The relationship between sine theta and sine negative theta, what's that? Sine theta equals negative sine theta. So sine of negative radical 2x, this just becomes negative C2 I sine of radical 2x. Everyone okay? Are we good? All right. Then let's just do, yes.
Technicality. Did
Technicality.
the algebra mistake earlier make any difference later on?
Oh yeah, it did, because I didn't have, like I had, see how I had the, yes, Heather, because I didn't have the negative in the argument.
But you had the negative in the there, which is what it ended up being anyway, right?
Yeah, but it's by luck
Yeah,
we
that's a good
got it.
But
That's just luck though.
Yeah.
That was luck. But yeah, good point. Good point. Are you ready? I'm going to combine like terms. Watch, I'm going to collect the cos radical 2x and cos radical 2x and factor out c1 plus c2. Ready? So here I am. E to the negative x, that's outside, times c1 plus c2 times cos of radical 2x. That's the two purple. Plus, same thing with the I sine radical 2x. C1 minus C2 times I sine radical 2x.
I just don't remember how to do this.
Okay? Now, C1 and C2 are just constants. I'm going to simplify my life here for a minute and say that C1 and C2, this is right here is just another constant. This is just another constant. I'm just going to call those K1 and K2. Okay, just to simplify things. I get now e to the negative x times the quantity of cos radical 2x plus k2 I sine radical 2x. Sasha, yes.
So the green equation on this portion.
Right here?
So
Yep.
the second part is because we changed C2 cos negative 2 root 2x to positive, that then the sign changes happen after that.
You mean how I went from here to here? Is that what you're asking me? Here to here, this line to this line?
Yeah.
Okay. The reason why cosine of negative radical 2x became cosine of positive radical 2x is only this reason. It's because you know from back in the day that if you have the cosine of theta and the cos of negative theta, cos of 60 degrees versus cos of negative 60 degrees, they're always equal.
Oh no, I just meant after that part, like the sign change from plus to minus.
Oh, here to here. Oh, that's because, I'll show you why. Because you know from back in the day,
Oh,
if
we
you
just removed the negative, okay.
well, no. So if I look at sine of negative 60 degrees versus sine of 60 degrees, they're always the opposite side. So this is only true if, watch, that's the case. So sine of negative theta here, this is just the sine of negative theta, becomes negative sine of theta. Okay? Now we are ready to do this, right? So the question here was, what does this all help me do? This, by the way, right, look at this, equals, right, so y equals, okay, e to the negative x times k1 cosine of radical 2x plus k2 I sine radical 2x. This is just another form of the general solution. But why do you care? Well, I mean, there's a big to-do, and at some point I have to decide homework on this, and I have no idea where you are in your textbook, but I'll figure it out. But what's interesting is, just like when you did vectors, right? You talked about vectors in component form, in standard form, in trigonometric form. There is a really convenient reason why we would ever want to express the general form of a Diffie-Q in this form. When you have complex roots, let me come back up and see if I can find it, right? The whole thing was, we called it R equals lambda plus mu I, okay? So let me come back down. R equals lambda plus mu I, okay? R equals lambda plus, hang on one second, mu I, and in this case it was -1 plus or minus radical 2I. Okay? You may now, moving forward, when you have complex roots, and let's tell the whole story. Complex roots of a characteristic equation that comes from a second order, homogeneous Diffie-Q with constant coefficients. That's the whole story. When that happens, you know that your general solution will always be y equals e to the lambda x, see, -1 times x, times constant 1 times cosine of mu x plus k2 I sine of mu x. You can skip all the derivation and go straight here. Spencer, yes?
For the R, it's going to be lambda plus or minus the mu I.
Correct.
And then you'll have...
Yes. So from now on, and this is incredibly convenient. I'm sure your text does a derivation of this. I'm also sure it's incredibly clumsy. In fact, can I just peruse while you're copying this down? Eric, I'm just curious. I'm sure it's clumsy. But now you know where this comes from. There is great utility in this version of a general solution. But again, let's not lose sight of where this comes up. Characteristic equation roots. What is a characteristic equation again? Don't lose sight of that. That is the reduced equation right here, okay? This was the characteristic equation. Where did it go? Right here. This is the, see how we know that always happens? This is the characteristic equation. When you have complex roots of a characteristic equation that comes from a what? That comes from a, right here, second order, homogeneous, diffie-q, with constant coefficients. Second order because second derivative. Homogeneous, set equal to 0. Constant coefficients, 1, 2, and 3. Okay, numbers. The obvious next question you have is, what if it's non-homogeneous? What if the coefficients aren't constants, right? That's all kind of the rest of the story. Okay? But now you know, I mean, all this mess, like look at this algebra. Oh my word. You don't have to go through it. There's no need to memorize this per se because you know how to get here. You can get here just working it through. I think there is something to be said for efficiency though. Just knowing if you have R equals lambda plus mu I, e to the lambda x times some constant, right? Cosine mu x plus I sine mu x. Okay? By the way, K1 and K2 are constants. What would we need to find the value of those constants? We need something. What would, yeah, 2 initial values, right? Which we don't have right now. Okay? Okay, yeah, the characteristic equation, Robbie, all that is, it's like, I think someone in here called it like, it's the useful equation that helps me solve it. It is this quadratic right here. Okay? Very good. All right. Choice to you all. Do you want to work one through all the way on your own from start to finish before I go on to the Wronskian? Do you want to do Wronskian now? What's your dealer's choice? Go.
If there is time.
If there is time, okay. Vote for the Wronskian. Raise your hand.
Is there
What is bronze?
New stuff or trial? There's just enough time for the Wronskian if we start right now.
Go.
New content versus practice on your own for one problem. Who wants to do new content? Okay, practice on your own for one. Okay, ready? Here we go. Wronskian.
Yeah.
All right. Recall. So, if you look, let's take a look at this. Consider the following. Okay? Consider f of x equals x squared minus 3x plus 4. G of x equals x squared, minus 3x plus pi. Okay? I could ask you right now, are these two functions linearly independent? Can f, for example, be gotten by multiplying g by some constant factor? Okay? Other question is, could g be gotten by multiplying by some, okay, no. So when you're asked to determine whether two functions are linearly independent, you can do it that way, which is just thinking about it. But there is something called, okay, the Wronskian, not to be confused with Gronkowski, who is a player on the Patriots. Although now that you know this word Wronskian, you can now say, like, what's Wronski with you? Okay. The Wronskian of f and g of x. Thank you, Nick, for laughing at my horrible joke. Okay? you can write it this way. The Wronskian of f and g, which is written abbreviation this way. The Wronskian of f of x, comma, g of x.
Is that just
Okay.
a funny W.
It's just a W, regular old W. It's the Wronskian, okay? This is how the Wronskian is defined. And I'm going to show you the Wronskian, show you what to do with it, why it makes sense, and then the proof of why this works. Like, I didn't just make it up. The proof is so straightforward. Just like the proof above here was very straightforward, it just gets very algebraically heavy. Do you understand? Okay? The proof of this is very straightforward. It's a little algebraically heavy. We may or may not do it. I don't know. Ready? Here is what the Wronskian W of f of g equals. It is, blast from the past. It is the determinant
Whoa.
of a matrix.
Oh my.
Oh, actually.
It is the determinant of a matrix.
Oh dear.
That'd be
Okay? It is the determinant of a matrix whose dimensions are, in this case, the dimensions here are, okay?
What's the order times the order?
The dimensions have to be 2 by 2 or 2 by 2. Why the number 2? The dimensions of the square matrix, this 2 and this 2, will always match the number of functions you are finding the Wronskian of. Okay? So you will never have a Wronskian of, for example, 5 functions where that matrix is a 2 by 6. That's not the definition of it. So the Wronskian of n functions is the determinant of an n by n matrix. Okay? It is the determinant of this matrix. Here are the inputs. Are you ready? It's the determinant of this. F of x, g of x, f prime of x, g prime of x. Yes, we're taking the determinant of a matrix whose entries are not numbers. Okay? Let's do it out. Let's see. Let's do it out. I'll meet you there. This is the determinant of, all right, f of x is x squared minus 3x plus 4. G of x is x squared minus 3x. Is it plus pi? Did someone catch me there? Minus pi, plus pi? Okay, plus pi. Very good. F prime is 2x minus 3. Okay. G prime is 2x minus 3. The determinant of a 2 by 2. Who remembers this from the days of
How long is it?
linear AD minus BC? What does that mean, Jeannie? What is AD minus BC?
Top left times bottom right.
Yeah, you multiply those two, right? So you multiply those two. And then what's the operation here?
Subtract.
Then you subtract what? These two, right? Okay? Let's make sure I meet you there. That's what that determinant's going to be. All right, I'll meet you there. Here I go, here I go, here I go. How do you multiply them, Eric? Oh, Eric. Okay, let's see. The quantity 2x minus 3.
Bottom two are the same, you cancel out, so we don't even multiply.
Right, don't even multiply it out. I agree, Spencer.
Wait, what?
Is this just to check
Because
that they're
there's
not
both
linear
factors
functions
of 2x
with
minus
each other?
3.
No, no, no. Well, yeah, you're going to see. Hold on a second, Heather. Yep. Because Heather's saying, like, what is this going to tell me? All right? When I subtract these two, right? And this is what he was saying. I'm going to factor out a 2x minus 3. Okay? And I'm left with x squared minus 3x plus 4 minus x squared plus 3x minus pi. Algebra. Watch yourself there. Okay? And we get 2x minus 3 times 4 minus pi, yeah? Okay? Notice the Wronskian here, okay, this is the big deal right now. The Wronskian, notice, did not equal 0. When the Wronskian of a set of functions does not equal 0, it means the functions are linearly independent. Okay? So, since... No, they are linearly independent. They are linearly independent. Since the Wronskian of f of x and g of x did not equal 0, that means f of x and g of x are what's called independent functions, or linearly independent functions,
Wait.
okay? Yeah, let me just finish writing it. Hang on a minute. Linearly independent functions. I'm loving this. Like, I'm loving this. This surface being able to like walk to the board both ways. Let me say what you should be thinking. You should be wondering, why does this not equaling 0 tell me it's linearly independent? That's the proof that I'll do when I see you next. It's very, very simple. It's just long and arduous, just like that. Do you have an idea, Max?
No.
Okay.
Wait. If x is a variable, couldn't you come up with some? Wouldn't 3 halves?
Yes. Okay. So great. So great. So great. Okay. Very good. So let's finish this thought. This is going a little bit to tomorrow. It doesn't equal 0. Okay. For all x.
So it would have to like actually just cancel out.
Okay. But story to be continued tomorrow. Max gave it away a little bit. All right. But right now, I want you to like say that. The but is ... We'll prove to you like why does this work? Like who like and if you're wondering why, like keep thinking about it. The reason why this works, I'll show you. It's very, very simple. It's just a more mathematically arduous, algebraically arduous proof. But that's the Wronskian. Go forth and don't do anything Wronski. Or I could say this. You know those pens that are in the dining hall? Have you seen those? The little pens you can get, they're little corns. The little plastic corn on the cobs. Oh, where did mine go? You can use them to write down little kernels of truth.
Oh my god.
That's cute.
If you have an ear for that.
Oh, wow.
Maybe that's too corny for you.
Wait, I'm a
Hey,
You are, isn't it?
Sasha, come on. Give me some laughs, Sasha. Toss me a few. Oh, everyone say goodbye to Oliver.
Bye, Oliver. Way to skip school. Screencast-O-Matic. That's such a good program name.
It's the best. It's the best. Oliver, class was short today because your classmates were talking about sex. Okay, bye.